Okay, so we're looking at different examples of equilibrium problems first. The first section in chapter 6 is all about the equilibrium model, which is just when the sum of the forces on an object equals 0. And I got a couple of examples that I think are helpful, but to be honest, just talking about some of these are good too. So number one, so for number one, we have, kind of like an example that we would used to do in the physics lab, which is where you have 3 ropes that are connected to a small ring. And we ignore the mass of the ring. 2 of these ropes anchored to walls at right angles. And so we want to know what the third one is. We want to know the strength and direction. And so looking at, looking at this figure, we've got 2 ropes that are, like I said, at right angles. T1 has a magnitude of 50 newtons. T2 has a magnitude of 80 newtons, and they're at right angles. The lengths of them don't matter so much, but let's practice drawing a free body diagram with this. So I'm going to hop on to the whiteboard. And we're going to start drawing this stuff out. Okay, so this is 6.1. Draw the free body diagram. Okay, so how are we going to draw the free body diagram? We did a lot of that on last week, with lots of different examples, but now we're actually going to be solving them. So we've got always just draw the axes first, label them X and Y, and then start drawing. So we have that T1 points this points to the left. And we had that T2 points straight up from our coordinate system. So qualitatively, at least, when you add these together, you should get something like, you should get a vector that points opposite to this 2. So if you imagine a vector that connects both of them, like T1 plus T2, the opposite of that should be T3. So I'll get rid of that. So you should expect that T3 kind of points down and to the right. And of course, that's what the picture is, but that's the point of this problem, is trying to figure out what that amount is. And also an important thing for this free body diagram is that F net equals 0. So always be writing F net off to the side as being 0. That way you know how to do it. So, so this is where we kind of stopped on chapter 5, where we had different forces causing an object to be either at rest, constant velocity, or changing its motion. Now, the next step is to sum the forces. So this is where we're looking at using the free body diagram to write down numbers. And so what we'll do, the most basic step that you can always take is to just write all the components for all the things. So this technically is in the x direction. So when I write parentheses x, what I really mean is some of the forces in the x direction, some of the components in the x direction. Okay, so this will equal T1x plus T2x plus T3x. And that, in this example, it equals F net in the x direction, but in this case, that's 0. So there's nothing wrong with just starting off with the most general way to describe it. And we can do the same thing for y. We're going to sum the forces in the y direction. Hopefully you're following along and writing it out as you're doing it, because it's one thing to watch all this stuff and you feel like you know it, but until you start writing it down, you might not actually know it as well as you think you do. So equals F net in the y direction, and that in this case also equals 0. Okay, so there's nothing wrong with writing it out like that. That's completely correct. Sometimes people, if they have more confidence, want to skip a couple of these steps, but this is the general way to start off. So now I would recommend, dropping some terms and then entering some things that you want to solve for. Okay, so in this example, T1x, right? T1x is -50. And actually, since we're here, we might as well just double check the numbers. Yeah, going back to the thing, yeah, T1 is 50, T2 was 80. All right, so let's write that, this simplified version. So T1x is going to be -50 newtons. T2x is pointing straight up, it's going to be 0. And then T3x, that is this one that we're trying to figure out. That is the x component of T3. And that's going to cancel with 50 newtons. So that's going to be, we're going to write it like this, plus T3x equals 0. So that's what the x equation reduces to. So I'm going to write, when I write these things, I'll write parentheses, I'll write a print x inside the parentheses. That is just shorthand for the sum of the forces in the x direction. And then in the sum of the y direction, you've got same thing. The 0, so the x component of T1 is 0. The x component of T2 is 80 newtons, so it's 80 newtons plus T3y equals 0. Then of course these two equations are decoupled, so you don't need to like solve one to get the other, as you will in many other examples. So here we get that the tension. So we get that the tension vector has two components. So it has T3x equals plus 50 newtons. These are vectors, so they need pluses and minuses. And T3y is minus 80 newtons. If I'm not mistaken, though, the problem is asking for the strengthen the direction of the rope, of the tension in the rope. And so you need to go a little bit further than this by, once you have the components, right? How do you find the strength of the vector if you know the components? Just Pythagorean theorem this. And so T will equal square root of T3x squared plus T3y squared so that's square root of 50 squared d newtons squared plus 80 newtons squared. I'm going to, just to keep the noise level down, you're welcome to unmute whenever you like to ask a question, but background noise can always be embarrassing. So the strength then, this is when you eventually just want to put it in your calculator. You get square root of 900, because 8 squared, so 80 squared is 6,400, 50 squared is 2,500, so 64 plus 29 is 8,900. So whatever that is. So square root of 8,900 newtons. Or, it looks like square root of 8, it's really 10 times square root of 89. You can, of course, factor out the, 100 in 89. So what's the square root of 89? So it's about 9.4 something. So I would say this is about 94 newtons. And then the angle, just off to the side here, well, you have to be careful. You have to be careful how the problem is asking the angle. If we call this angle phi, then theta would be then phi would be the inverse tangent of what? 80 over 50. So 80 over 50. And that's the answer. You can work it out and make sure it's in degrees. Okay. Anybody have any questions or comments on this problem? Again, you're feel free to unmute at any time. This is a simple kind of warm-up problem of how we want to go through these examples. Okay, so I will even, let's see, I will even save this. Oops. And then we'll move on. All right, let's do another one. So let's go back to our book and see what problem might be interesting to do. Yeah, this one's kind of similar. Number 2 is kind of similar. A couple of these other ones down here I thought were kind of interesting. One that I typically do is number 4. A 20 kilogram loudspeaker is suspended 2 meters below the ceiling by ropes that are both 3 meters long. What is the tension in the cables? And they're at equal angles, actually. What is the tension in the cables? So number 4, let's do number 4. This one is helpful to draw a picture. And here we have to make the free body diagram ourselves. 6.4. So you read the textbook on these model solving or the model and problem solving strategies. I would always draw a picture first and then draw a free body diagram from it. So because the angles here are pretty important. So it's 2 meters below the ceiling, but the ropes are both 3 meters long. We got the loudspeaker and it's a mass of 20 kilograms. And so let's just make sure we have the free body diagram right. Let's see, the free body diagram then drawing it the same way. Start with Y, X. We don't know the tension in these cables. We know the mass. And so if we know the mass, then we know the gravitational force. Right, that's the first one we should write down. So that's mg, straight down. And these two tensions are going to be equal in magnitude, but they're going to be pointing at different angles reflected around the y-axis. T, also T. I'm going to do it a little bit more generally because you might have a homework problem where you have different angles. You'll have a homework problem where you have two tensions that are at different angles, and you'll have different tensions. And oops, sorry. And you'll find out the easy way to remember is that the rope that's shorter usually has a lot more tension in it. So summing these forces, the x direction. Let's see, we have theta with respect to the y-axis. So that's going to make T1, it's going to, the x component of T1 is going to be minus T1 sine of theta 1. Again, we'll drop the subscripts because they'll be equal, but I'm trying to do it generally. And this will be plus T sub 2 sine theta 2. And that will equal, 0, because we forgot to write down F net. F net in this case is also 0. Very good. What about in the y direction? Notice all those signs, and I'm keeping all the signs consistent. Anything that points to the left has a negative. Anything that points down also has a negative. So, how do we sum the forces in the y direction? Well, sometimes people like to start with minus mg. That's fine. So it's minus mg, and then the other two will be plus. Will be plus T1 cosine theta 1. I'm kind of run out of room, aren't I? draw it a little bit smaller. Plus T1 cosine theta 1 plus T2 cosine theta 2, and that equals 0 as well. So that's summing the forces in both directions for this example. So when you know that the tensions and the angles equal, then this first equation becomes redundant, and you just need the second equation. So so if T1 equals T2 and theta 1 equals theta 2, then X equation becomes redundant, and then the Y equation becomes minus mg. I'll look at the other terms. We've got, it would just be a t cosine theta plus t cosine theta. And so that would just make it 2t cosine of theta, 0. But we don't know theta, and so we're trying to find t. And looking at this equation, we don't know, we can plug in for 20 for the mass, we can plug in 9.8 for g. We're trying to find t, but we don't know theta. And that's where we look at the problem where we were given the dimensions. We were given that the height was 2 meters, and the length of each of these ropes was 3 meters. Okay, and so these angles that we defined were this. And so oftentimes you have to find the correct right triangle to make the problem, which in this case, in looking at this right triangle right here, we have that for this angle theta, the hypotenuse of the right triangle is 3, and the adjacent side to the angle is 2 meters. And so this is just another example where we don't need to find the angle explicitly in order to find the cosine. Sometimes some of you are thinking, well, okay, well, I should find theta. Well, how would I find theta? Well, I know that the hypotenuse is 3 and the adjacent is 2, so let's try maybe do the Pythagorean theorem to find out that this side is like what, radical 13, and then it's to the arctangent of radical 13 over, kind of saying this out, but you can imagine how you would do this. If you'd have 3 and 2, then, well, no, that's not radical 13, that would be radical 5, right? Because you square everything, and that's how you get it to equal. So technically theta equals inverse tangent of radical 5 over 2, and then the cosine theta, right? So then the cosine of the inverse tangent of radical 3 over 2, you know, we get into this habit of wanting to find the angle, but we just get 2/3. And so you can certainly do that. You might get some round off errors. You certainly won't get a nice 0.66666 on your calculator. But we didn't need to know the angle to find its cosine. All we need are a couple of sides of the right triangle. And that's a very common thing in physics, being able to find the cosine or the sine of an angle without knowing the angle itself. And so we'll just plug that in. So let's go ahead and plug in all the numbers here. We got minus 20 kilograms times 9.8 meters per second squared. Plus 2t times 2/3. And that all equals 0. So we could solve it algebraically, or we could just plug in all the numbers. You get about 150. And if the weight was actually 200 newtons, then we would get 150 because look, T is, I mean, that's a 4/3, and so T is actually, oops. Yeah, T is actually 4/3 of G. Right, solving everything, it's going to be, or not 4/3, 3/4. 3/4 times mg. Hopefully you can see when I did that. So 3/4 of 200 is 150. 3/4 of 196 would be 149. I think so, yeah. Because 3/4 of 196 is 3/4 of 200 minus 3/4 of 4. So it's actually 147. And that's how you do number 4. So an example with another equilibrium example. Both of these are static equilibrium because the particles weren't moving, but summing all the forces and finding a final result. I can save this one as well. Once I find my thing. Oh, there it is. Okay. These are examples of equilibrium problems and where you don't need other formulas for the forces. Those are good when you're first starting out. Eventually, real force problems will have forces that are quote unquote unknown, and you'll have to know how to find the other forces. So let's do an example like that. If I can. Oh, geez. Okay. There we go. Let's go back to the book. So yeah, the rest of these 6.1 equilibrium problems, they're all helpful to work out. The Newton's second law problems are where we're going to have an unbalanced result. Okay, 8:55. Let's see. One that I like to do that's really, it's just practice with summing the vectors, is this one right here, where number 9, where you actually have the forces. You have all the forces and they're on this incline, and we're trying to find, acceleration. Okay, so this is good practice without identifying forces. This is assuming that you know the magnitudes of all the forces acting on a 2 kilogram object, 2 kilogram mass, and we're trying to find a sub x and a sub y, the x and y components of acceleration. So this one, the work is already half done for us. We've already identified all the forces, and now we just have to sum them and really just do it directly. And we want to do it along the x and the y axes that are tilted. So let's remind ourselves of some of these numbers. So 2.82. If you think that's a strange number, you'll see in a minute why they chose it. And then it's 3, right? Okay, so let's write this one out. Again, even if you have the free body diagram already, it's still a good idea to write it out. So 6.9, where we have tilted axes, x, y, and so we've got a 3 Newton force that points up the x-axis, 0 newtons. We got a force that goes up the y-axis, magnitude 2.82, that one backwards of magnitude just 1, and all those point along the tilted axes. And then one that points straight down of magnitude 3.0 newtons. And that one is the only one that's at an angle of 20 degrees. Of course, they all have different labels, and just double check that. Oh no, they don't have labels. We just had to make them up. Okay. So let's just work starting from the one on the X, call this F1, and then call this one at the top F2, call this F3, call this bottom one F4. So to do this example, and we know that the mass of this object is 2 kilograms, 2.0 kilograms. So let's start calculating. Let's start summing these forces. In the X direction, again, there's nothing wrong with writing all the components out. F1x plus F2x plus F3x plus F4x equals F net x. That's correct. And when you're learning it, that's actually really helpful. If you can kind of observe that some of these are going to be 0, well, you can try writing them out. So it'll be this should be F1x, F2x is 0, so this will be plus F3x plus F4x. Now this is going to equal m times ax. Ax might be 0, it might not, we don't know. And then same thing in y direction. Now we have F, trying to make F's not point that much, F2y. So 1 and 3 components are not in the y direction. They don't have components in the y direction. So it's F2y minus F4y. And that equals also m times a sub y. Anytime we have subscripts, like x and y subscripts on the symbols, that means that they're vectors. So all of these symbols, notice how I didn't say like, oh, I guess I did it here. Notice how there's no minus signs here. All the negative signs and the positive signs of the vectors are contained in the symbols themselves. So for x, yeah, I got plenty of room. This will turn into 3.0 newtons. That is F1x. F2x is 0. F3x is minus 1, minus 1.0 newton. And then we have to do a little trick. We have to do 3 times cos or sine of 20, because once again, even though this is in the negative x direction, looking back at this free body diagram, the x component of it, I know I'm writing on the 20, the x component of it points in the negative x direction that we established. So it'll be minus 3 times sine of 20 degrees, and that's going to equal 2 kilograms times a sub x. And then similarly for the y direction, this will be F2y, which is plus 2.82 minus now 3.0 times cosine of 20. And that also equals the unknown acceleration, 2.0 kilograms times a sub y. And that's how you solve the problem. The only thing we have to remember is if you work it out and plug in the numbers, you find that, not surprisingly, 3 times cosine of 20 is 2.82. You know, to significant figures or whatever. So we actually get that a sub y is 0 in this case, because 3.0 times cosine of 20 is approximately 2.82. And so we get that a sub y is 0. And what about a sub x? We have to just double check what the, let's just double check what 3 times sine of 20 is. And I'm doing that real quick. At least I should be. Let's see. Just a minute. Does anyone want to quickly calculate 3 times sine of 20? I actually think it's close to 1.
Mm, 1.02.
Perfect. Thank you. I'll double check that. All right, so 1.02. So if it's 1.02, then we've got the x direction becomes, thank you very much. The x direction becomes plus 3 newtons minus 1 newton minus 1.02 newtons, which, you know, just round up to 1 sig fig. So you get actually just plus 1 newton, a positive 1 newton. So all the forces in the x direction add to a plus 1 newton. So F net actually points up the x axis, which means now that the acceleration in the x direction is, of course, F net in the x direction divided by m. Trying to be as detailed as I can, plus 1.0 newtons divided by 2.0 kilograms. We all know that. That's going to be, but this is physics, so we have to make sure it's the right answer. It's plus 0.50 meters per second. Very nice. So those are a taste of some exercises in the textbook. I will say this as well. Get rid of that. Well, actually, if you wanted to take a couple minutes to copy that down. I actually want to do some harder problems. And we have some time. We have about 15 minutes left. There are these discussions about mass, weight, and gravity in the textbook. I certainly have a lecture about that on my playlist. So rather than trying to go through that, I think it'd be better to just do some more problems. And certainly I want to do ones that involve friction. So yeah, because being able to identify the friction force is really crucial. So let's go to some more samples. Okay, so we're back on our list using Newton's second law. Mass, weight, gravity. Oh, there's a calculation. Let's look at number 16 real quick. Caught my eye. The position of a 2 kilogram mass is given by x equals blah, blah, blah. 2t squared, or sorry, 2t cubed minus 3t squared meters. Where t is in seconds. What is the what is the net horizontal force on the mass at some later time? At time t equals 0 seconds times 1 second. No, this is pretty straightforward, hopefully. I don't like assigning problems like this actually for number 16. Here I can. And in this case, all you would do is you take the derivative twice of the position to get acceleration and then multiply by mass. So, right, so the formula for the second derivative of a power is just n minus 1, you know, times a thing times to the raised to n minus 2 power. That's not that interesting. So that's why I don't like assigning problems like that, because it's just more practice with just calculation. But it's still helpful to see. So number 15, spaceship is at rest in deep space. Its thrusters provide some amount of thrust, at a force of 1200 newtons. Spaceship fires its thrusters for some amount of time. Okay, well, this one's actually not that hard. 20 seconds, then coasts for 12 kilometers. Oh, wow. How long does it take the spaceship to how long does it coast? How long does the spaceship take the spaceship to coast at this distance? Okay, this one's actually, number 15 is actually not that bad. Before I jump into friction, this is just practice with the equations. So 8.0 times 10 to the 4 kilograms is our mass. And then we have a thrust of, and it's at rest, deep space, so no gravity. Deep space always means no gravity in these examples. And we have thrusters with a force of 1200 newtons. So, 1200 kilonewtons. That looks a little more realistic, actually. And the spaceship fires its thrusters for 20 seconds. Then coasts for 12 kilometers. Okay, so the question is how long does it coast at that 12 sun? Let's set this problem up, because this is a good one that actually combines kinematics with dynamics. And it's really worth discussing because that's the whole point of force. So let's do the problem first. 6.15. So draw a picture. Oh, there I am. So draw the rocket. I'll scooch this over a little bit. Yeah, let's draw a rocket. It's going to be pretty innocuous. That's my rocket. And, you know, if you're trying to figure out what coordinate system to use, to me, the easiest thing would be to just assume, you know, that it starts at the origin of some x-axis. Okay. And at time t equals 0. Yeah, this is fun. Let me just, I was going to do the friction, but I just decided to do this one because it's got a lot of pieces in it. It's got forces and dynamics in it. So this is 0. And this is some location x1 at time t1 where its thrusters stop. And then we have a equals 0 here. So then what looks like we're trying to find, so x2 at t2, but yeah, so, you know, the mass of the thing, and it's got a thrust force. So that's kind of the picture during, yeah, that's kind of the kinematic, yeah, it's kind of the kinematic picture. What's free body diagram? Well, the free body diagram is very straightforward. I mean, it's just the thrust force. So if I were to write the free body diagram, I would just do this. That's it. And that, of course, is F net. So summing the forces in this example isn't really a big deal. It's just F net equals MA. Or sorry, well, that's always true, but in this case, it's thrust force equals MA. So in the X direction, we got nothing in the Y direction, we got thrust force equals M times AX for that first 20 seconds. And so if you remember the numbers, it'd be 1.2. So 1200 kilonewtons is 1.2 times 10 to the 6 newtons. And we had a mass of 8.0 times 10 to the 4. So this would be 8.0 times 10 to the 4 newtons. And that equals, or times a sub x. This should be plus, since it's pointing in the positive x direction. And so now we just have to take 1.2 divided by 8. That's going to be 1.5. Let's do the scientific notation. That we got 1.2 times 10 to the 6 divided by 8 times 10 to the 4. This is something you really shouldn't need to do on your calculator, because this is like 12 times 10 to the 5 divided by 8 times 10 to the 4. Units and so forth, so newtons per kilogram. I guess that's a way to think about acceleration as a Newton per kilogram. But 12 divided by 8, like I said, is 1.5. And so it's 1.5 times 10, right? Because the 10 to the 5 and 10 to the 4 cancel. And so we get an acceleration in the x direction of plus 15 meters per second squared, right? Yeah, SI units, good. And that's going to be for 20 seconds. And so now what we want to do is, since we know that this displacement is 12 kilometers, what this problem was asking for was the time it takes. So what we're really trying to find in the notation is T2 minus T1. But once the thrusters are fired, we're back to a uniform motion model. Zero force, zero total force, actually really no measurable forces. So T2 minus T1 would actually just be X2 minus X1 over that V. Minus X1. So 12 kilometers divided by V1. Hopefully you can see it. This is like V0, 0, like T, X, and V0, 0. Got that acceleration, which is 15. And so now we see why we do forces, okay? Because forces give us a way to determine acceleration. Okay? Acceleration is arguably the most important thing in dynamics and kinematics, because it tells you how the motion of an object changes. Like velocity is important too. If you know the motion, then that's great, but the acceleration tells you how it changes. So let's work it out. And we just need to find V1. So V1 then will just be, using one of the kinematics equations, it'll be V0 plus a T1 minus T0. There's two time intervals to keep straight. This is 20 seconds. And so this is just 0, starting at rest, plus 15 meters per second squared times 20 seconds, which again, this is something you can do in your head. 15 times 2 is 30. So 15 times 20 is 300. So the V1, that is the velocity of the rocket in this X direction after 20 seconds, is plus 300 meters per second, or if you like, 0.30 kilometers per second. Because, you know, if you go back to up here, your displacement, the X2 minus X1 is 12 kilometers. And so if we want to get the correct unit of time without carrying an extra conversion factor, you have to make sure these are both in kilometers. So this is 12 kilometers divided by, I don't know if you can hear my son in the background, 0.3 kilometers per second. Once again, this is another thing that you don't need to calculate. You can just take 12 divided by 3, which is 4, 12 divided by 0.3 is just, which actually both of these have positive signs on them. And so the time is just scalar, so you get 40 seconds. Oh, good, very nice. I wasn't planning on doing this problem, but this ended up being really good because it shows you the point of forces. We'll be doing problems where we just spend all this time identifying forces, but at the end of the problem, we want to use the forces to know how the object's motions change. Forces give us a way to understand how the motion of an object changes with this simple example. Questions, comments on this one? Well, I'll go ahead and save this as well. There's certainly not much time to start a new problem. Hopefully we did enough examples to where you feel a little bit more comfortable with identifying these things. I have all the whiteboard PDFs saved. And so I can certainly post those to Blackboard. Yeah, going virtual has its advantages, has disadvantages. Of course, so this week we'll just do this. So we only really meet 2 more times. So Wednesday, what we'll do is we'll do friction. We'll do plenty of problems with friction, and really looking at the free body diagrams. And again, I'll, like I said, handpick problems from the textbook. Notice that I also, as I said I would, I changed chapter 6 homework to be due on Friday. And I also moved chapter 7 homework to next Wednesday. That way we get a little bit more time to work on these things. And chapter 8 homework, I'm just leaving as it is. So we do have chapter 7 reading quiz that I'm just leaving right there, due tomorrow. Okay. Questions or comments from anyone?
I'm okay, thanks.
Okay, well, thanks for your time, everyone. I had a lot of fun doing these problems. You know, this is the best way to learn physics. It's just by doing problems. Listen to all the videos in the world. You can read the textbook, which certainly is part of it, but ultimately working those things out. So really be using my opinion, you know, having taught this stuff for well over 10 years, my opinion is that treat the end of chapter exercises as the main way for you to learn it, okay? Because the tests, you know, as you can tell, the tests are kind of on the level of the exercises at the end of the chapter, okay? The homework is kind of on the level of problems, the more general ones. So that's the best place to learn. All right, well, if nothing else, thanks for your time, everyone. We'll see you here tomorrow.
Thank you.
Thank you.
Bye. Yeah, you too. I'm gonna go ahead and end the meeting. Take care.